in the previous slides. So the idea here is that I'm going to replace a split water molecule by a dielectric constant. Instead of having all the molecules present, we reduce a lot the CPU cost. So this is the whole idea. So all the approximations that are here, if you take an ion, we know that it's going to be electric cloud. We know that the Pauling principle should apply, so you cannot overlap these two molecules. A simple way to do so is to create a spherical particle, as you can see here, where we put a central charge. So this is one of the approximations. And the second one is, as you can see here in this picture, we have a split model, and then now we replace it by just a median. So we average out all the main properties of water. So this is one of the critical approximations, or one of the approximations that's done. And the reason to do is because it decreases a lot the CPU cost. I mean, I'm showing here a picture where you have a protein, you have all the water molecules, and you have the ions. When you go to the implicit description of the solvent, the continuum model, you end up in something like that. And just to remind you something that someone just asked me, the CPU cost is proportional to the square of the number of interactions that the sites of interaction that you have. So if I decrease a lot the number of particles, of course, the CPU cost is also going to decrease a lot. So this is really quite important. And one of these, let's say, classical example of the continuum model is this Thumford-Kirkwood model. In this case, you try to use the crystallography data, so you can see that you keep the position, the coordinates of the titratable groups, and you put everything inside a spherical object where you define layers. So number one is the protein itself. Number two is up to this point the solvent can come, and up to the 3 here is where the ions can come. So using these parameters, you can identify different median. There are, of course, lots of problems that Thumford and Kirkwood introduced. For instance, they don't provide a clear clue for what dielectric constant you should use for the interior of the protein, and also how it should be this transition, or where we should place this boundary. So this is not clear, and if you have taken an electromagnetic course, you know that at the boundaries, the electrostatic potential can explode to minus or plus infinite. So when you change the size of A or B, or in particular, sorry, the size of B in this case, you can see that the results can change a lot. So there are problems that were introduced, but anyway, the idea of the model has been there, and it's, let's say, it's the base of several methods that have been done in the electrostatic field. So that's why it's important for you to get to know. I'm not going to all the details, because the math can be tough for people that are not familiar. But this is the paper where they publish. I mean, it's a quite old paper, 57. So if you were interested, I mean, you can read this paper. And probably to understand this paper, you also have to go back to the former paper from Kirkwood that was published in 36, something like this. Okay? So just to try, I mean, to get a feeling of the model, the idea is here to write the free energy. And then you can split the electrostatic part in 3 contributions. One that's related to the Coulomb interactions, the other that's related with the solvent contributions, and a third one that comes from the solved. So this is the simple way. I mean, of course, I'm oversimplifying things here just to give you a feeling, but at least I guess you can get the main ideas of the models. And one thing that happened, like when you were working here with the solvent, is that very often you have to use Legendre polynomials. So in this case, you can also see that we have a summation here that in principle should go to infinite. And that's also another problem. When you are trying to do this in a computer, and if you are trying to calculate interactions, and it happens that they are very close to the boundary, the number of terms that you need to put in this summation can be quite high. Just to give you an idea, if you are, let's say, 2 angstroms apart of the surface, you need the problem to incorporate something like 10,000 terms. So the CPU cost, of course, is going to be quite high if you'd like to use this model. So that's why often we use lots of simplifications, and one of the things that ideally everybody would like to try is also to use a uniform dielectric model. Because if you use a dielectric model that's uniform, it means that this dielectric constant difference here is going to be equal to 0, so you get rid of the b's and you simplify a lot. And it's good because it seems to work for several applications. Actually, it's one of the most, let's say, polemical views of this field. That there are people that they see as a religion that you should work with a uniform medium description. Others that they see as a religion that they should work with a dialectic interface. But in fact, we don't know where to place, and we don't know exactly which numbers we should use. So at the end of the day, what people typically do is like they try and they use this as a kind of a fitting parameter. So it's something, I mean, to keep in mind. I often prefer to use a uniform description where B disappears, so I can decrease my CPU time. And if I succeed to benchmark experimental data, I'm very happy because I decrease a lot the cost. I can run my simulations for many more Ks longer, and that's something that helps a lot as well. To give an idea about how you can use the model, we can go back in history. So one of the applications that people have been using is to study here, as you can see, calcium binding proteins. So here you have a calbindin, you have 2 calcium ions, and you have the complex here. And I can show here the chemical equations that can translate this process. And it's nice to see that when you do a comparison, for instance, for delta pKa's as a function of the salt concentration, and you compare experimental data with the results from Stanford. In the dashed line, you have the Stanford circuit. The experimental dates are the dots, and they seem to agree to each other. So at least you can get a very reasonable description of your system. It's not perfect, but you can capture the main physics of it at a very low CPU price. By the way, this has been done with a uniform description. So you can reproduce ionic strength effect, I mean the salt effect, using a uniform description of the solvent. And if you're curious to know, I mean, the solid line in this case is the results from Monte Carlo simulation. So you happen to be able to describe salt effects for the wild-type calcium binding proteins using such models. This is a typical experimental data that you can see in this field, one of the historical papers. Just to know, I mean, how the charge affects, you can investigate for proteins where you change in ideal models the charge, where the Stanford circuit is going to break it down. I mean, this is an approximation. It's a linear approximation of the Poisson-Boltzmann, if you prefer to look in this way. So for relatively moderate charge proteins, it agrees pretty well with Monte Carlo simulations. When you start to increase too much the charge, then you see a departure of the results. So you can go a little bit better if you have the nonlinear version of the Poisson-Boltzmann instead of the simple Stanford circuit approximation. So if you're working with proteins or under pH conditions where the charge of your proteins are not that big, the Stanford is particularly good. As I said, the uniform dielectric is something that's very polemic, so it's important for you to be aware that there are other groups that they show different results. Here's an example of a work where they show using atomic simulations, how should be the translation that's not going to work well if you have just 2 parameters, like the Stanford circuit model. So there are different groups working with this, and they have, I mean, different views. Depend, again, also what you are after. The results, I mean, if you try to use 2 parameters, so this is what often people are doing. I mean, if they try to describe vacuum, they use 1 for the light constant. If they just like to have some kind of solid description, they use something between 2 to 4. If you'd like to put more, let's say, degrees of freedom in the problem, like rearrangements, people use something between 4 to 10. If you have more internal rearrangement, you go to 10 to 20. But you can see it's not really clear what number you should use. I mean, something between 10 to 20. Okay, 11 is fine. But maybe you say 19, whatever. I mean, you can make a choice because you are just trying to use, as I said, a kind of input parameter that better is going to reproduce your data. And in fact, I mean, I have done some exercise about this a while ago, and you can see if you take one protein and you use all these descriptors to see the quality of your results when you're comparing your Poisson-Boltzmann predictions with the results from, in this case it was a Poisson-Boltzmann, with the results from the experiments, you can see that very often there is an ideal condition that's not really between 10 to 20, for instance, that often people use. For instance, for this protein in particular, it's going to be a little bit larger, the dielectric constant would give you a better result. So if you work in a very low number, as you can see here before the blue dashed rectangular area here, you can see that your error would be higher if you are working in these conditions where you are better than the new model. Remember, we all the time try to be better than the new model that are represented here by the gray dashed line. So if you're working with a dielectric constant that's smaller than 10, your results are much, much, much worse than you can get with the new model. Again, if you're working in a high dielectric constant, depending where you are here, it can be slightly better. I mean, the difference is quite small. But anyway, you can see that there's a tendency to be better or to tend to be worse, depending which number. So this is, again, in my view, a way to tell people that, okay, this is just a fitting parameter. So if you use a uniform and you reproduce well your experimental data, you should be happy with it. So the basic ideas for the Poisson-Boltzmann, I'm not going again to all the equations. I mean, I have here in my slides all the equations, but I guess for the sake of time, I'm going to jump. But just to give you a feeling, I mean, if you have not heard about this before, what we do is to combine the Gauss law that often we use the so-called the Poisson equation. Here you have the charge density, so the charge divided by the volume of a given object. You have the dielectric constant, and you have the electric potential. So we jump here. We also have the Boltzmann distribution. So how is the distribution of charge as a function of separation distance? And you assume here that your particles are point particles and they don't interact with each other. So doing so, you have this exponential contribution here. But pay attention that there is a catch here. When you are working with the Boltzmann description, what I have here is not the electric potential, but is the potential of mean force. So we have two different descriptions that at some point, when you are going to combine the Poisson description with the Boltzmann description, you are going to assume that they are equivalent, they are equal. This is so-called mean field approximation. So it's there where you introduce some approximations in the Poisson-Boltzmann description. So just to make, I mean, this story a little bit short, that used to be the class that Roth used to offer at this school some years ago, at least he was doing it. You might have a very nice description of all these things in the YouTube. So just to go a little bit quicker, so we throw away the size of the particles, as I said, and you combine everything, I mean, the distribution in the Poisson equation, and doing so, you end up with the Poisson-Boltzmann equation. But again, remember, when we did this operation, we made this approximation here. That's the mean field. And that's why we are neglecting the so-called ion-ion correlation effects. And ion-ion correlation effects can be also important for part of the phenomena that I explained in the very beginning of my first class for this attraction on the wrong side. I mean, the negative and the negative. I'm back to this point soon. So we're done. Sorry, I'm just flashing because I tried to delete the slides and it didn't work. So I'm jumping here to don't spend the time with these things. And then we can go to the key parameters. That's really what I'm going to use later. So in this field, I mean, there are, let's say, numbers that can be, they tell you something before you do any kind of analysis. One of them, of course, the ionic strength. And that's the definition of the power of the salt. The other is the bi-Hooker screening. In this case, you can see how much the ionic solution, I mean the salt particles, are decreasing your electrostatic interactions. So the ideal behavior that I showed you before can be recovered if you are working, even if the 3D structure of the protein, in a very high salt concentration. As much as you increase your salt concentration, so as much as you have a large number here, you decrease the attraction or the repulsion of the system. At some point that you end up in the ideal behavior. So you can recover the ideal behavior in a very high salt concentration. Another parameter that's quite important here is the so-called Biedron length. In this case, you are checking or you are getting an estimation for the power of the solvent to screen out interactions. So water at room temperature, for instance, gives you a number of 7.2 angstrom. So that's what you're going to get from the Biedron. So these are, let's say, key parameters that tells you a lot about the system. Okay, back to the Poisson-Boltzmann, just to illustrate to you, there are different ways the numerical part can be also very much elaborated. I mean, I'm just giving you some examples of the main techniques, and I'll just select pinpoint one. That's probably the most useful one. There is, by the way, also a poster outside, so you can get more information about the Poisson-Boltzmann approach. But just the idea here is like you calculate your electrostatic potentials in different resolutions. You start with a very coarse description, and you start zooming in the protein, and you use the previous information as input for the next level, and this is a way to get the potential in different points of these grids, and that's the information that you use to predict the electrostatic problems. If you'd like to try and do an exercise, there is a paper that was published many years ago by Martin Karplus that happened to also be one of the Nobel laureates in '98 or in 2013. And in this paper, they have all the data that you can use one of the codes that is publicly available called MIAD to reproduce these results. So this is an exercise for home that can be good. But if you prefer to use other tools, there are also APBS. It's probably the most common for people that are familiar with a PyMol, for instance. Or if you'd like to go online, you can use H++. So in this case, you can upload your protein coordinates, like the PDB file, and you get lots of electrostatic properties, including the pKa's that I was talking about. All these are for free. It's nice to make a comparison between the Poisson-Boltzmann approach and traditional Monte Carlo or molecular dynamics simulation. So I try to make this comparison here. In terms of the molecular simulations, you can probably get an exact solution, and the reason is because you're not invoking the linearization or the ion-ion correlation that you were taking out. So all that approximations that I showed you, they are going to be present in this mean field approximation. It's more stable, the numerical solution of Monte Carlo, for instance, than the nonlinear form of the Poisson-Boltzmann simulation. Here, you can define the protein concentration as an input parameter, while here, you assume typically an infinite dilution. There are ways to correct it. For instance, change your Debye-Hückel parameter. You can write down your Debye-Hückel parameter for another way, that you incorporate the function of the protein concentration as well, but it's not often done. Typically, if you are working with molecular simulation, when you increase too much the salt concentration, the number of particles of your system also increases in the same proportion, of course. And this means that your CPU cost is going to be much more high. On the other hand, in the Poisson-Boltzmann, it's just a parameter, so it's not going to hurt. But it can break down if you have divalent or tetravalent ions, especially because you have these ion correlation effects that you were neglecting. Often, simulations are time-consuming, while the Poisson-Boltzmann can be memory-consuming. You saw the example before where you have all these grids. And depending on the size of your protein, you need a large number of these grids, which can mean that you need larger memories. And as you can imagine, an approximation should break down at some point. This is an old data where they were measuring osmotic pressure as a function of concentrations, charge density. And you can see that in the case of divalent ion, monovalent ions, it's pretty okay. They agree more or less with each other. Of course, as much as you increase the charge, it's expected that they start to deviate. I already showed you the results from the Tanford curve, where you could see something similar. But if you go for divalent ions, not just they change the numbers, but also qualitative, you can get different predictions. The Poisson-Boltzmann is going to predict a repulsion, and using Monte Carlo simulation and also experimental data, you can see that should be attraction. So depending on what regime you are, the Poisson-Boltzmann approximation is going to break down. One way to look for it is this parameter here. This was proposed by Roland Netz some years ago, I would say more or less 20 years ago, by the way. And it's so-called the electrostatic coupling parameter. What it tells you? Well, you have here, first of all, just a number. Here we have the valence with the power 3. So if I have a monovalent ion, it's going to be 1 power 3. If I have a divalent ion, it's going to be 2 to the power 3, and so on. Here I have the Biron length, so water at room temperature, as I just told you, is 7.1 power 2. And then you have the charge density, the surface charge density here. So if this number is closer to 0, you don't have ion-ion correlation effects. So the system behaves like you were expecting. Positive and negative should repeat each other. Positive and positive should repeat each other. Positive and negative should attract each other. The basic Coulomb law idea. But when this number here, it starts to be very far away from 1, it's where you are going to observe this weird behavior of the system, this peculiar phenomena. It's where, for instance, you have ion-ion correlation effect. So to have ion-ion correlation effect, according to Roland nets, you should have this number larger than 1. And as you can see, if I increase the valence of my contra ions, by the way, this is the valence of the contra ions, you can see that in this case, if it goes from 2 to 3, for instance, we are talking about a large number now. And now you start to deviate, and this is what you are observing here. So to deal with the calculation of these guys, I mean, of course, one way would be to use Tanford, the other way would be to use Poisson-Boltzmann, but there are new methods that have been appearing, and every time there is a new things. I'm just trying to illustrate a bit what's out there, and you can see that there are, let's say, 3 main classes. One is the one that they're using molecular dynamics, that's coupled with any kind of constant pH methods, and in this case, we have a time dependence. We can also have a Monte Carlo method, so you take away the time dependence, and you have empirical methods and together with AI. If we try to see how these things have evolved, I mean, I try to organize in this picture, you can have a more colloidal-like description that reminds you even the Tanford-Kirk approximation. I mean, this is actually the Tanford-Kirk approximation. So depending on what you are doing, I mean, what kind of transformation you're doing, what kind of, either you're introducing a new feature or you're eliminating one, you can end up into methods. I mean, there are, of course, lots of details to describe here, but the main idea is like you can incorporate or not some details depending on what you were after. So one of the methods here, that's the FPTS, the one that we have been developing, and that's the one that I'm going to more details describe it to you. But there are, of course, other ideas that I'm going to describe a little bit more superficial, how you can couple it with, one method of this with traditional molecular dynamics, and that's what we call the constant pH simulations. But this is also evolving, and you have other approach as well, and I should maybe even say that now this combination with AI, that should be in this picture as well. So this is, to give an overview and to show that the number of options that's out there is quite large. And again, to pick up which of these cases depend all the combination of things that we already discussed. So start, to classify things, let's go to one of the initial ideas. This is the work that I already cited to you as a landmark work. And the main, let's say, it's very simple the idea if you really look in a superficial way, because the idea is like you have a molecular dynamics. From time to time, you are going to call a titration scheme. In this case, it's a Poisson-Boltzmann solver, the MIAD that I already cited to you. So I have a Poisson-Boltzmann solver here. So I pass from the molecular dynamics trajectory the coordinates and the charges. I run the Poisson-Boltzmann, I get an update of my charge, and I plug them back in my MED simulation. So doing so, I keep changing my charges according to the pH and according to the local environment. So the neighbor effect now is present in MED. This is completely different than you just launch your MED simulation where you provide the PDB. Eventually, if you're careful enough, at least you run something like PropKA or H++ to update the charges as a function of the pH that you like to study, and then you run your MED. Here, what I'm saying is that pH is an input parameter, like you have a temperature, like you have a pressure. And then the simulation is going to define, during your simulation run, what should be the protonation state for each point of your trajectory. Depend on the neighborhood, depend where is the solvent, where is the salt, all these kind of things. So this is what they have started. Actually, for me, it's one of the most important work to establish this coupling. There are, of course, things that we can discuss here that can be critical sometimes, or things that often we pretend that's not there. For instance, when you do this coupling, you are assuming that the first field description that you have here, that was parameterized using eventually or more often physiological conditions, should be the same parameters if you change the pH. This is, of course, something that we assume that's true, but has not been proven to be true. And honestly, we all know that if you change too much the conditions, you expect to change your parameterizations. But you keep the same first field parameters as the simulation was supposed to be running at pH 7. So this is something, to also remember. There's another thing in this kind of approach. For instance, here I can have an atomistic description of the solvent. So I can use a explicit solvent. And here they are using Poisson-Boltzmann, which means a continuum model. So the solvent is not described in the same level. That's another thing that can affect the results. But come on, if you look to the benchmarks and what they are able to do with these models, it's amazing. So it seems that all these approximations, at least for the studied systems so far, is not being that critical. There are other strategies. I mean, there is one that's called the lambda dynamics, where you introduce in your Hamiltonian an extra particle. Again, I know that some people, this can be very much far from what they are doing, so that's why I'm not going into all the details, but we can discuss with you afterwards if you'd like to go to a little bit more steps. But the point that I mean is important from all these equations, so don't be afraid of this equation, but the important point is just to show that in most of the applications, the protonation change, I mean the change in the protonation states, is all the time a phenomenological description. As you can see here, you incorporate this free energy term in your Hamiltonian, and that term is essentially depends on two input information, the pKa zeros that we discussed in the first class, and the pH of the medium that you provide as an input parameter. So this is all the time a phenomenological description. In other words, what we are doing here is to assume that the main changes are only in the environment. And that's, I mean, you change here in the environment. You see how the displacement of the particles have changed and how they have changed your normal Hamiltonian. And then you put like just chemical contribution as a phenomenological description. So, for instance, a molecule that has an area that's very close to the solvent and the same titratable group that's very deep in the protein is going to remain more or less the same in this description. So you're not really taking account that the environment has changed drastically. So this is something that is probably an artifact, or can introduce artifact in most of the approaches. There are many other approaches. I mean, I'm just citing a couple of more papers. I could go on. I mean, I'm sorry if you work with another method that's not present here, but the list has increased a lot over the years. And I mean, just to illustrate to you that there are different flavors that you can make a choice here. But there are a couple of things that are common among most of the methods, and that's why it can be challenging, in particular when you are trying to work, for instance, with protein-protein interactions or protein-polyethylated interactions. One thing that has been critical is how long it takes for you to have these simulations converted. So you can see that conversions has been a trouble. Although when you make a comparison between calculated and experimental data, the agreement is often reasonable. Look here that for this simulation, it took about 10 nanoseconds for conversions. So you spend quite some time of your simulation, depending on the size of your system, to get conversions. And I'm talking about a single protein. So if you're going to do protein-protein interactions, you can see that this problem is going to be much more complex. So that's why we have also to think about more coarse granular descriptions that we can get a better conversions. This is another method. I mean, they are using a dipeptide. Come on, just two monomers, two amino acids connected to each other, and look how much time they need for conversions. 40 nanoseconds, which is quite a lot. Okay, when they're doing modeling, and if you'd like to go for this pH description, we have to think about how we can get a better description of the whole thing, at the same time reducing the CPU time. So you know that in this case, electrostatics, I mean, we are assuming for this that should be the main driving force, because pH is an important thing. We know this equation that I'm going to describe you tomorrow, but in short, it's what is going to help us to understand this complexation on the wrong side. And you would like a model that should be able to describe these main features: pH, ionic strength, and mutations. Another thing that's important here is we'd like to get free energy as a function of separation distance. And if you have been working for simulation trying to get free energies, you all know that free energy is really very painful. I mean, it's time-consuming, it's harder to converge, it takes longer. Sometimes we have to think about different tricks, like go for metadynamic, this kind of thing. So if you can find a way to get this in a cheaper CPU time, at least that can be a good estimation. You are going to be say, okay, thanks. And that's what we are trying to do. There's another feature here that often you need to repeat the calculation a lot. So if you pay a high price, this is not going to allow you to run more and more case. So you need also this compromise. And there is another thing that can be very critical, especially if you are in Latin American countries, budget. Actually, I think this starts to be a problem in different places as well, that we're not used to have it before. But anyway, it's, we have to think that if you get simplifications that can still let you play the game, they are going to be very useful. So these are the things that we were in mind, and it was using these things that we have been playing with all these models over the years, I mean, that can be used for different applications. So these are the models that we have been working for different purposes, and we are trying to make our zoo of spherical cows. One of the models is this one here that we call 40, and is the one that we use for protein-protein interactions. So a constant pH simulation that can be used for protein-protein interactions. So just to give you, I mean, a couple of examples to you, this is one of the earliest models. I mean, we have a protein here that we can use an atomistic description. So the inputs could be the PDB, could be, on the old days, which was a molecular homological model, could be from AlphaFold, whatever you want. We confine everybody in this spherical cell, and in this case, we can have explicit ions, as you can see here, and it's coupled with a proton. The original model comes from the Swedish guys, Magnus Uner, Bujan, so they have been working a lot with this model. And the whole idea here is like you can also define a protein concentration. So when I confine everybody here inside the simulation box, I can define a radius. If I know the rate, I know the protein concentration. So we can introduce protein concentration effects. And if we'd like titration, we have to couple it with a proton box. So proton can go to the solution, or to the protein, and vice versa. So it's a semi-grand canonical approximation if you prefer. That's the original idea and the original equations. You can see that pH, again, is a phenomenological description, so it enters pH there, and I also need the pKa zeros as an input parameter. So as you saw in the lambda dynamics and most of the techniques, the pH is a parameter, is an input parameter, but we have a phenomenological description. So the pKa's, I mean, just to give an example of the source of the pKa's here. And that term that you can see in green is where we are going to observe the changes in the electrostatic interaction. So randomly, I'm going to come here to the protein and select by random amino acid that if it has a protonaceous state, I'm going to try to take the proton and put in the solution, and I use these equations to define if I'm going to accept or reject these movements. And the acceptance is going to be based in two factors: the changes in the Coulombic interactions with all the others, and also these chemical contributions. So depend what numbers I have here for the red and the blue terms, the same change in terms of the green part, the Coulomb interactions, can be taken a different way, because depending on the conditions, it's going to be easy, this process. In other conditions, it's going to be forbidden. And we can do the opposite process, to take a protein from the solution and try to put in the protein. So this is a simple way to do a titration of protein, and to get the net charge of the protein as a function of pH, and all the properties of the amino acid as a function of pH. And if would you like to have a titration plot to get the pKa's, what you have to do is to run this calculation in different pH conditions. You make a titration plot, and from the titration plot, you get the pKa's for whatever you want. Or you can get the isoelectric point if you'd like to look for the whole protein. For polyelectrolyte simulations, we can adapt the old model. Essentially, you repeat the same things, but now you add a bound constraint terms. So we make part of the ionic particles that were free in the solution. Now they are connected by a harmonic spring. Depending on the constant of this harmonic spring, we can make something stiffer or more flexible. And doing so, now we can study a protein polyelectrolyte interaction. So essentially, we kept the same idea. We can do a titration, etc. But now I can introduce a polyelectrolyte chain in the model. But there are problems. If you try to study protein-protein interactions with an explicit ionic description, so you try to move, there's going to be lots of ion particles. So it's very hard for you to be able to sample the whole thing. At some point, you try to move and you get stuck. It's more or less if you take the metro here and you try to go to the train. There are lots of people that is going to be around you, so it's very hard to move. So it was actually inspired in this situation of the metro that we said, well, what about if you just put the effect of the people, but don't have the people over there, so we can move quicker? And so the model that I showed you originally was like that. You can see the explicit particles here. And we'd like to replace not just the water now by an implicit description, but we also would like to replace the ion effect by description that could get rid of them. So we came up with this model that's, I'm simplifying here, and I'm going to detail right now. But the idea is, like you see, it's really a better or a coarser version of the previous coarser version model. And doing so, we could reduce a lot the CPU cost and get rid of this problem when you try to move, that we end up stepping one of the particles that could prevent the acceptance in a Monte Carlo simulation, for instance, of the movement of these two particles. So the main motivation to come up with a new model was, in fact, to apply it to study protein aggregation, protein complexation studies. So this is the beginning of what we call the FPTS. Again, just remember the equation that I showed you this morning. So if you try to take the equations and now, instead of just activities, we remember that an activity is this factor here, the activity coefficient, times the concentration, and we write down the terms. We can play a little bit with the math. We can calculate the log. So that's what I did. And then we can start to identify who is who, like minus log of Ka is the definition of pKa. Minus log of the activity, that's activity here is the concentration times the activity coefficient, is the definition of pH. And then we are left with these terms. So we can arrange these things in different ways, and easily we can identify that the first term is just the free energy to go from the protonation state to the deprotonate state. So now we can get inspired by this and write down our function, our Hamiltonian, that essentially is the changes in the interactions and minus these phenomenological descriptions. At this point, now we have to make a choice. How am I going to calculate delta E? And it's exactly here that we invoke the Tanford-Kirchhoff model. So FPTS is quite simple. I mean, it's essentially basic physical chemistry course for first-year undergraduate students. And now, looking to the equation that you saw in the Tanford-Kirchhoff model, we got rid of the B's because we made the model as a uniform solvent description. We can write down this essentially as the Coulomb law. And the way to put salt was using the classical chemical potential definition. So we end up with this expression where here we have the electrostatics, the delta E in the previous slide, and here we have this phenomenological description for pH effects. That's all. That's the FPTS. And if you'd like to see the results, I mean, that's the comparison between the implicit and the explicit model, which honestly, since this was more than 10 years ago, all the time that I look to this data, I have to look to the captions, because I don't know if the plots with symbol, the curves with symbols are the FPTS or the other way around. Because you can see that the agreement is quite nice for charges as a function of pH, the charge regulation capacitance, that's a quantity that I'm going to introduce you better tomorrow, but essentially is the charge fluctuation, and the dipole moments, they are very close to each other. So these are comparisons between the two theoretical models, or let's say two of our spherical calls, if you prefer to take like that. There are some differences when we go here for the dipole moment of a more elongated molecule like lactoferrin, is one of the milk proteins. In this case, we can start to see some deviations. But let's see to the benchmark between experimental data. So there are three proteins that are very often used in benchmark studies. So here I have HP36, BBL, and one of the lysozymes. You have here the experimental data, predictions from our atom simulation, our implicit method, I mean FPTS, and the GB approach. That's another approach that's also done in the simulations. And if you look to the common metrics that are used, I mean, you can see that the best results are the ones from an approximated method here, GB. That's the one that comes closer to the experimental data. Our data, use the implicit model, can also, on the average, be equivalent. It can give some larger deviations, but you can be surprised that if you run a full all-atom simulation, at a constant pH simulation, the results are worse. And they take much, much, much longer. So you can see the comparison here. I mean, the errors in the experimental data, compared to the experimental data using all-atom simulations, is worse than we can get here. On the average, I mean, that's for sure. If you look at all the trajectory, it's 0.2, and here has 0.5 and 0.5. There are, of course, troubles to reproduce. Oops, this is wrong direction. Let me, okay. There are troubles to reproduce some specific amino acids for all the techniques. As you can see here, this GLU35 from lysozyme gives trouble to all the methods, either under or overestimating it. And it's probably related to the fact that we are using that phenomenological description where we are assuming that the environment is just changing part of the things and not the whole thing. If you try to benchmark this, I mean, of course, you can select different protein data, I mean, different data. We just took a couple of data that was available at that time, and we did a comparison with PROPKA, by the way. And we can see, I mean, that it was very nice. I mean, at least for this specific set of proteins, we were quite happy. Both of the methods, I mean, they have deviations for different amino acids, but in general, FTS gives, for at least for this set of proteins, as I said, a better result. I mean, we are doing, I mean, just look at how you analyze the regression coefficient and the slopes of these plots, and we're good. Another advantage is the fact that the simulation is quite fast. So if I compare FPTS with Poisson-Boltzmann, you can see that we are orders of magnitudes quicker for a larger protein as this one that you can see in this PDB file. I mean, the CPUs were more or less equivalent, and we are talking about 2 orders of magnitudes in terms of CPU performance. The method has been extended to RNA as well. The results are equivalent, so I'm not going to describe all of them to you, but believe me that it's more or less what you saw for proteins. And then I'm back to what I showed you at the very beginning. I mean, remember this transformation. So if I have these proteins, I know that they should have this conformation as a pH effect. So how I can know if from my ensemble of proteins that AlphaFold provided me, I have the right structure? Well, this is one way. You can calculate the electrostatic free energy for the stability of your proteins. And in this case, you can see that you can easily identify the one that's supposed to be more stable in a given pH condition. And what we did here was with FPTS, but you can use Poisson-Boltzmann, you can use any available tool to do exactly the same. So if you have a set of proteins and you like a set of conformations that you took in your ensemble from AlphaFold, and you like to make a clear difference between which one belongs to which case, you can do this using electrostatics. The tricky thing is using the ordinary version of Fold for at least the top 25 cases. We didn't get the one at the other pH condition that was 7. So if you get diversity in your AlphaFold structure by different things, and there are different options out there, eventually you can classify them and see if the one that you are looking for your specific pH conditions can be there. But my take-home message from this part is exactly this. It's really the combination of physical methods with artificial intelligence that can bring us to the next level. As you can see here, if you just using AlphaFold, you're not going to be able to make a difference between them. But somehow, if you find a way that AlphaFold can provide you a diversity of structures, you can select them. For the case of insulin, you could do it. I mentioned to you about conversions that most of the methods have, and the advantage when you simplify things is that you decrease the CPU costs. And you can see here that the convergence is quite quicker. I mean, we can get reasonable numbers, in this case, with 10 to the power 4 Monte Carlo steps. And if you look about this in terms of CPU time, it takes seconds. So this is appealing. I mean, of course, these molecules that I'm showing here, they're not that big, but it makes this, it makes now possible to apply this for protein-protein interactions. So that's the other advantage. And another thing that we have done, I mean, is to couple this with molecular dynamics. So instead of using MIAD here, we can go back and put FPTS. So that was the whole idea. I mean, we take a molecular dynamics and we replace MIAD by FPTS. We also made a choice for the molecular dynamics part, in particular to use a force field where the solvent description was the same. So FPTS works in the continuous description. And we needed to find a force field that would work in a continuous description as well. Thanks to Philippe de remote teams, I mean, Fabio Stepone and etc., they have this OPEP force field. And even more, OPEP has a version 5. And in the version 5, they also have ion pairs. So it was easy for us to switch on and switch off ion pairs depending on the pH. So everything was ready to just be coupled with a titration scheme. And this is the beginning, what we call now OPEP6. But unfortunately, it's not always better to put more details in the model. You pay more CPU, and at the end of the day, you don't get too much more. So this is a good comparison, I mean, where we can compare the results of FPTS that you can see here, the traditional one that I just showed you, and the results with OPEP6, where we are coupling molecular dynamics now with titration. Remember, FPTS is a rigid description of a protein. OPEP6, we have the conformations change as well as a function of pH. And it happened that the results that we get from OPEP6 are not always better than what you can get from a rigid description. If we compare even with the methods that are quite simple, I mean, you know that this Go-like model, you get the parameters to reproduce the crystallography data. So this is the class of molecules that we call, models that we call Go-like models. So you know, you really make sure that your parameters are going to give you the proper solution. Essentially, that's the idea. And even so, I mean, FPTS can be better than these guys. Look at the comparison here with this one. OPEP6, of course, is better than these guys, but we are not so better, for this protein at least, than FPTS. So this is something I mean to keep in mind, that we always have a tendency to try to put all the details in the model. It does not mean that you are going to improve the results. Sometimes simpler is better. I'm jumping. Okay, now we can start a bit of this peculiar phenomenon. I think I can already start. If you, I can go to the, and then start anticipating you a couple of things that I'm going to say on Saturday. So the first thing that it's a bit contradiction. I mean, if you ask people, can like charge attract each other? If I ask you here, I mean, have you seen any case before that a positive particle would attract a positive particle? Who has? You see, we can count 2, 3 people. So this seems to be a contradiction. But if you ask nature, it shows that it's true. I mean, this is one of the classical examples. If you take actin and actin in the presence of monovalent ions, they repel each other. Actin is this white-like molecule here. But if you put just a high valency contraion, I mean, just change the valence of the contraion, they start to attract each other. So going from +1 or to +3, you change completely the regime. I mean, we had repulsion, and now we have an attraction. And this is experimental data. I'm not talking about simulation. I'm not talking about any crazy theoretical math. It's just a simple observation that you can do in experiments. The only difference is the high valency. If you'd like to go more, I mean, you can look into this paper that was the cover of Physics Today several years ago, where they show that you can fit DNA inside this small capsid here. And you have to remember that DNA is a highly charged molecule. So how on earth you can make something that looks like a spaghetti around this little thing here, can fit inside that object with all this strong electrostatic repulsion? If you are working with protein-protein interactions, you can see that I can take 2 calmodulin. So I'm talking about a protein that in the study condition has +24 units of charge, and the other that has +24 units of charge. And they happen to form a complex. Or, sorry, actually calmodulin should be -34, but never mind. It's just the same example, 34. You can see that the free energy as a function of separation distance, I mean, we have here free energy, separation distance. When I change the valency from -1 to -2 and -3, it starts to be more and more attractive. The only difference is, again, the valence of the contraions. You can do something similar playing with the dielectric constant, by the way. But I mean, never mind. It's just to give a feeling to you that it's possible to see an attraction of 2 like charged objects, either in the experiments or either in a theoretical calculation, like you can see here, just playing with the valence of the contraions. There are many more examples. I mean, of course, there is no time to go through all them, but just to give you an idea about what's happening, is like is more or less to take about two argon particles that eventually your particles, they start, to correlate and concentrate in one region, and this give you a kind of instantaneous attraction. It's possible to go to the statistical mech and demonstrate that essentially what you have is like an energy particles attracted to others. But anyway, you can see this, not just in biological materials, you can see this in cement, so materials in general. So if you talk with Oliver, probably he has many more examples where you can see this in material science. And again, is an ion correlation effect. So if you change the valency, you can see attraction or repulsion. Cool, right? Okay, I'm not going to all the details, but let me go now to the next event that, to try to organize this idea. I already make a comment to you about the coupling parameter, the electrostatic coupling parameter. So you can see here simulations where you have micelles, colloidal particles with minus 60 units of charge. And as you increase the valence of the control ions, can you see that they start aggregating here? And if I go to trivalent, they really form a high cluster. So here you can see the transition between the regimes. And it's the electrostatic coupling parameter that's telling you if they should be in this behavior or this behavior. When we are with the valency of 1, we are here. So they obey even the DV-LEO theory. So they should repeat each other if they have the same net charge or the same sign of the net charge. But if we go to this regime here, the valency has increased, and now we can see attraction. So this is what we knew, or that was, let's say, the common knowledge for people that were working in the field around the beginning of the century, until new experiments appeared. So later, people start to see this weird behavior. I have here pectin, casein, and I'm mixing up them together. What you are having here is the net charge as a function of pH. There is a condition where one is positive and the other is negative. And this is natural for you to understand that they're going to attract each other because one is positive and the other is negative. But look at what happened at this condition where both, in this pH window here, where both molecules are negatively charged. They form a complex that's also negatively charged, but they attracted each other. And the critical point is, they have done these experiments in monovalent salt, which means that Z here is 1. And to make everything worse, they also have performed experiments very often when the proteins were at the isolectic point, which means that this guy here is 0. So the coupling parameter is 0. And according to the electrostatic coupling theory, it should be the weak coupling. So it should be a repulsion. But they observe attraction. How can we explain it? It's not ion correlation. For ion correlation, I need a high valency. But what about this case? We can see an attraction. Well, as usual, there are, of course, lots of discussions, and many more experiments were performed. I'm just picking up another one here. Again, it's the interaction between polyelectrolytes and another protein, and you can see that they observe exactly the same thing. In this region here, we have soluble complex where the molecules are very close to the isolectic point. So I have even situations where the attraction should not be electrostatic. If you think about, let's say, basic ideas, because they are 0 sometimes. You can say that's van der Waals. Yeah, but van der Waals will not be enough. So there were lots of debates about these things. There were lots of experimental data, lots of things. Of course, we're not going to all the details. One of the theories that was actually suggested was that somehow the protein should have a kind of a patch. So this is a good example. They have done a simulation where they show here that for this protein, there is a large concentration of charge with opposite sign of the polymer. So this could be an ion dipole interaction. So you can see that they were mapping here with these points here, the center of mass of your polyelectrolyte. And there is a large concentration of them really in the area where you have these patches. So this could be an argument. But come on, ion-dipole interactions, they are weaker than charge-to-charge interactions. And if you put salt in the system, the screening factor, we can see it, look into the exponential contributions of this that you use in the mathematical equations, is going to be stronger. So it does not make that sense. But then if you look very carefully to the model, there was also a van der Waals term. So maybe the van der Waals was too strong, and that's why they could see this mechanism. I mean, this has been around for a while. I mean, you can see the papers that they are more or less 20 years ago, and I mean, the explanation comes to this paper, and that's probably a good beginning for tomorrow. Okay? So I keep your attention, and I hope if you're curious, you came tomorrow to see the end of this story. And it's tomorrow that I'm going to show you the case of the antibody design and protein-protein interactions related to virus. Okay? I'm happy to take your questions. So, yes?
Apart of all the course grain that really speeds up the simulations, how the constant pH compares with polarizable force fields?
They are doing different things. I mean, the polarizable force fields were explored one mechanism, and the pH effects are explored another one. So ideally, you should combine everything. I mean, ideally, we should treat the pH effects using quantum methods. The problem is the CPU cost. So you need, I mean, to find a compromise. I mean, I would say if you are going to work with problems where you know that, like you have calcium, you have magnesium, you have divalent counterions, and the ion correlation is not going to be the main issue, but you like to explore this kind of mechanism like polarizable effects, then of course you go for polarizable models. But if you need to explore pH effects, then you go for pH effects. And if you'd like to study, I mean, protein polyelectrolyte or protein-protein, you have to see if the CPU cost is going to allow you to really to get the free energies. Maybe if you have one specific case, one specific condition, one physical-chemical conditions, then you can go to a more detailed level and you can explore much deeper the system. But if you'd like to try different mutations, for instance, that's the case when you were trying to optimize an antibody, for instance, then it's not going to work to do, I mean, all these very expensive simulations. But maybe at some stage, you have to convalidate your data using more sophisticated methods or more costly CPU time. My point is that always you have to see what is better for what you're doing. I mean, there is not really just do this method and you are done, or do that one that you are done. Each case is one particular decision. Maybe there are better alternatives. Once you have it done, it's easier to see, then you can improve. Maybe your choice is not the ideal and you have to step back. I mean, it's always the case. Okay? Good question. I mean, thank you, because it's allowed me to make these comments. I think this is very important for a school. I mean, sometimes we are working a project and we are discussing, we are going very deep to our own problem, and we forget that there is much more out there. So we believe that the only way to solve a problem is using our own tools. But our own tools is just part of a big universe. We have to see how we combine these for specific questions. And for me, the most important thing is to make sure that your biological question, in this case, or your, let's say, your scientific questions, is really very clear. I mean, you know what you are looking for. If you don't, I mean, there are people that they have a tool and try to find a problem. I think it should be the other way around. We have a problem, and should find a solution for it. And we should see the tools that are better for that particular problem. Any more question? Okay, so if you'd like to see the continuation of this story, welcome tomorrow. Okay, thank you. I guess, Rafael, now we have lunch, right? I don't know how it's going to be organized. We have to talk with Thiago. But if I understand correctly, we might have some sandwiches. Yeah, because I think the canteen is closed. And yeah, so let's see.